It's a real pleasure to welcome all of you to the main building of CERN. Yesterday we were in the gateway, and I think the rest of the conference will happen in this building. And it is a real pleasure to welcome Juan Maldacena once again, and he will going to be telling us, as you can see from the BFSS conjecture, a review. Please, Juan.
Hello, can you hear me now? Okay, so the organizers have asked me to give a review of the BFSS conjecture. So the BFSS conjecture says that M-theory scattering amplitudes are equal to the lran limit of a certain matrix quantum mechanics. So all references in the talk are hyperlinked, so if you want to look at the talk later, you can find all the references there. So we'll review this conjecture and related issues, and it won't be historical, but hopefully it will be pedagogical, mainly targeted for the under 50 people who have not seen this in the beginning. So first, let's start with some comments on M-theory, some hopefully well-known comments. So M-theory is a theory of quantum gravity in 11 dimensions, which reduces to 11-dimensional supergravity at low energies. And it's also supposed to reduce to type 2A string theory when compactified on a very small spatial circle. When the circle is very tiny, we get a very weakly coupled type 2A string theory. Now, M-theory can be obtained from various limits. So we could start from that type 2A string theory and think about the strong coupling limit, where we'd get M-theory in a bigger circle. We could also obtain it via this BFSS conjecture, which is what we will review during this talk. And also, we could get it by taking the lran limit of some other compactifications, such as, for example, ADS4 times S7 or ADS7 times S4. If we use the dual field theories and then take a suitable lran limit, we could also get this 11-dimensional theory. So the BFSS conjecture is one of the angles we have on this theory, an important angle. So we're interested in the theory with asymptotically flat space boundary conditions. So we have R1, 10 at infinity. And the main observable we're interested in is the S matrix of massless particles. So we have massless particles coming from infinity, interacting in the central region, and then going all the way to infinity. And I want to emphasize that we're interested in the full non-perturbative amplitude. So that includes, for example, amplitudes where we have particles that come in, form a black hole. The black hole evaporates. It emits massless particles. And then at the very end, everything decays back into massless particles, and we have massless particles at infinity. So we have this S matrix, and the objective is to calculate this S matrix. Now, if there were other stable particles, we would also have to include them in the S matrix to get a unitary S matrix, but in M-theory, we do not expect other stable massive particles, other stable particles other than the massless supergraviton multiplet. Now, so we're talking about these full non-perturbative amplitudes. So they are functions of the momenta of each of the particles. And for now, we are only making the statement that we expect these amplitudes to be well-defined observables of quantum gravity. So we are only assuming asymptotically flat space boundary conditions. In the middle, we could have anything, like we could form intermediate black holes, which have a different space-time geometry. Now, in this transparency, we're just reminding you of the light front coordinates. These are just some coordinates you could choose that will prove convenient for what we will do. So we can select two of the coordinates, call them plus and minus, and then define the corresponding p plus and p minus. So here, when you do Lycon coordinates, convenient to take the momenta with the index down. It's negative definite, so minus p plus and minus p minus are both positive definite. And the massless dispersion relation takes this form. And if we view x plus as time and p plus as the minus p plus as the Hamiltonian, then this looks very much like the dispersion relation of a non-relativistic particle of mass minus p minus. Okay. So this is just simple kinematics. Now we'll do a certain tricky operation, which is to compactify the x minus direction. So we take that x minus coordinate and we make it compact. Then that implies the corresponding momentum will be an integer, and since minus p minus had to be positive, then this integer has to be positive also, or non-negative. Now, note that the amplitudes we would get in the theory where x minus is compactified are in general different from the amplitudes we would get in the uncompactified theory with those particular values of the momentum, right? So this is now a new problem that we need to understand. So this null compactification can be is such that because the circle is a null direction, the actual size of the circle is 0. So we are compactifying on a circle of 0 size. Now that can be viewed as the limit of compactifying on a circle with spatial size and then taking that size to 0. Now a small space-like circle is the same as type 2A string theory at weak coupling, and momentum along that circle correspond to these 0 branes. And so carefully working out this limit, this is very simple. It's just tracking down the small size limit and tracking down the amplitudes. You find that the amplitudes in the compactified theory are just the same as the low energy limit of a certain scattering problem involving these 0 branes. So, and these are computed using the theory that describes the low energy limit of the 0 branes, which is a certain matrix model, okay, as known from the work of Polchinski and Witten. Okay, so we understood then that the compactified amplitudes, the amplitudes in the compactified theory, are equal to the amplitudes in this matrix model, a certain scattering problem in the matrix model that we'll discuss in more detail later. So this follows simply from this M-theory type 2A relationship, and this is not yet the BFSS conjecture. So this is just essentially almost by definition of the small circle size limit. Now, the BFSS conjecture is the following. It's the idea that if you take those amplitudes of the compactified theory and then take a large n limit and large radius limit so that we are keeping the ratio n over r fixed, the p minus fixed, then we will get the uncompactified amplitudes, okay? The amplitudes of the uncompactified theory up to some simple volume factor whose origin we'll explain later. Now, the intuition is that if we were to form a wave packet that is, let's say, localized in the 11th direction, then we have the scattering occurring at some localized region, and the fact that we are compactifying shouldn't matter too much, especially when in the limit that the circle becomes very large. Of course, with the kind of states that we have plane waves, so with fixed momentum, and so again we expect that the scattering will happen at some localized point along this x minus direction. And because the wave function is spread, we have some simple volume factors, which were the origin of this simple factor we had here. So that's a simple kinematic factor. Okay. So now we'll define more carefully the matrix model and the type of scattering problem we have in this matrix model. So the matrix model is, again, the low energy limit of the 0 brane theory. That's the same as the dimensional reduction of 10-dimensional super EM mills to 0 plus 1 dimensions. So we have 9 matrices. They are n by n Hermitian matrices. And we'll also have fermion. So we have 16 fermions. And we have this relatively simple Lagrangian. It's simple in the sense that it's completely determined by supersymmetry. And it has this interaction term involving a commutator. And then there is also this related Yukawa term. So that's the Lagrangian. It has an SUN gauge symmetry, or UN gauge symmetry. And the gauge field only appears in the time derivative. And the only role of the gauge field is to impose a UN singlet constraint. So we could think of this as a model with a UN global symmetry, and then we impose the UN singlet constraint. And it's only on those, once we impose the singlet constraint, that we have the 16 supersymmetries. Now, we could consider the U1 sector, so that is the matrices that are proportional to the identity. And the interactions vanish for those matrices, and we get this simple Lagrangian that looks like the Lagrangian of a non-relativistic particle plus some decoupled fermions. So if the energy of the SUN part of the matrix was 0, we'll discuss that later, but let's for the moment assume it's 0, then this U1 center of mass degree of freedom has this simple non-relativistic action. And the role of the fermions is to fill all the states of the massless supergraviton multiplet. And then this is just simply the superparticle action in Lycon gauge. So we are getting the same as all the states we have in the massless supergravity multiplet from the center of mass degree of freedom. Now, it's believed that the SUM problem has a single bound state with 0 energy. And the potential, so remind you, the potential had this commutator term, and diagonal matrices have 0 potential. So the potential has some flat direction, so roughly has a shape like this, where the flat directions are the commuting matrices. And then, in principle, one expects a continuous spectrum, and we'll discuss the continuous spectrum later. But the idea is that there is a truly normalizable 0 energy state that is localized in this, let's say, central region of the potential. And the wave function decays as you go into decays as a power as you go into these other flat directions. Now, the evidence for this is some index arguments, and somewhat subtle because of these flat directions. And we also have results on how fast the wave function decays for large R. Now, so let's now discuss the low energy states, so the states of these matrix models at low energies. So we said that the potential vanishes when the matrix is commute. And so we can, let's say, diagonalize the matrices. And just as an example, let's imagine a matrix which contains 4 blocks. Each block to lead in order is just a diagonal matrix with a diagonal entry, which contains an identity matrix of matrices of n1 times n1, and so on. And then we separate them. We make the xi very, very large, and their difference is very large. And then within each subblock, we put one of these 0 energy bound states that we discussed. And so the idea is that that state that we get in that way would describe 4 gravitons with momenta in the null direction proportional to ni, okay, to each of these ends. So this is a way to construct the asymptotic states of the matrix model, of the matrix scattering problem. So in general, this n by n matrix will separate into n submatrices where the center of mass coordinate is very far away from all the others. So that defines the asymptotic states in this scattering problem, and it gives an n graviton asymptotic state. It's something that will be identified with the n graviton asymptotic state. And then the scattering problem involves a situation where we have, for example, in this particular example, we have a 2 to 2 scattering amplitude. So we have initially a matrix containing only 2 subblocks where the xi's are, the x1 and x2 are very separated, but then they come close together, they form a general matrix, and then it splits again into 2 other submatrices with perhaps different values of the ni's. Of course, the total rank of the matrix should be the same, and that's just the conservation of the momentum in the null direction. Now, we define the scattering problem in the matrix model, and now we'll restate the BFSS conjecture. So the idea is that we take that. So in the matrix model, we have these asymptotic states, and we have quantum mechanics with flat directions in the potential. So we have a natural scattering problem in quantum mechanics. And the idea is that the Larsen limit of that scattering problem in quantum mechanics is the same as the scattering amplitudes in M-theory. Now, there are various subconjectures. So the first one is that this limit exists. So it's non-trivial that you take this limit and the right-hand side doesn't blow up or doesn't do anything strange, doesn't start oscillating, and so on. And the particular behavior that the scattering problem has in order to reproduce the scattering amplitude, in particular, so for example, it should go to 0 as r goes to infinity, and that's not obvious. So it's necessary for the conjecture to be correct, but we don't have a way to a priori say that that's how this limit should behave. That's as an example. Now, in addition, the limit should be a suitably analytic function of the momenta, of the p-minus momentum. So the p-minus was discrete, but then should become a continuous variable after we take this limit. Then the result should be fully Lorentz invariant. So these amplitudes in the compactified theory, they are not Lorentz invariant, and we should gain the full Lorentz invariance after we take this limit. Then the S matrix should be unitary in the Fock space. So the total probability. So now the S matrix is obviously unitary in the matrix model. So the matrix model is an explicitly unitary system. So one might naively think that it's obvious that the other one will be unitary. But this is not completely obvious because it could be that you produce many, let's say, low energy gravitons, so gravitons with n, let's say, of order 1, which were not the kinds of states that, let's say, survive in this limit, which we are supposed to have n going to infinity. And if the total probability of producing such states with n's that are finite was a finite number, then we would not get some amplitude that will be unitary in the Fock space. And in fact, some of the authors of this conjecture think that this is indeed not the case, so that the full amplitude will not be unitary. So here there is kind of a split among the authors of the conjecture. But well, this is, I think, let's say, more conventional expectation is what I'm stating here. But well, this is an open question. It hasn't been proven. Now, in addition, so these are some of the subconjectures, but of course, we also expect that it has all the properties we expect from M-theory. So it should reduce to the supergravity amplitudes, it should contain membranes, it should contain fibrils, it should contain black holes, and so on. Now, the fact that it contains membranes actually can be relatively easily seen. And in fact, this matrix model was used to describe membranes before BFSS made their conjecture. So the idea is simply that you look at this term and you consider configurations where the commutators are non-zero. An example of such a configuration would be the following. So suppose you take 3 of the x's and you make them proportional to SU2 generators of dimension n. Okay, so some spins suitably large so that you have n-dimensional representations of SU2. And in this situation, then the commutators are non-zero, and you get a spherical membrane with some variable radius proportional to lambda, this lambda of time. And in this way, you can indeed check that you get membranes with the right tension and so on. Now, one can also consider some very simple scattering situations. And so one can consider scattering of D0 branes at low velocity and large distances. And this is related to the small momentum transfer limit of amplitudes. And so in this situation, we consider particular scattering configuration at long distances where there is no transfer of null momentum. And In this situation, as a first approximation, we can consider, again, these asymptotic states that do not interact with each other. But then we have these diagonal matrices, and the off-diagonal components are massive particles, are massive modes, sort of massive W bosons, let's say. When we integrate them out, we generate certain interactions. Naively, we might expect to generate a potential. And now that vanishes by supersymmetry because of the cancellation between bosons and fermions. In general, you might expect some contribution proportional to the velocity squared. And that also vanishes due to supersymmetry. And the first correction is a correction that goes like the fourth power of the velocity. So it's a v to the fourth correction over and proportional to r to the 7th, 1 over r to the 7th. And so that's the leading interaction that we get in this highly supersymmetric theory. And this leading interaction is, reproduces what we expect from graviton exchange. So that's what we get from integrating out the massive modes at one loop. Okay? Now, if we consider even higher loop corrections, then we expect further corrections going like n over r cubed. So this is sort of the Toft coupling in this configuration. And those, if they were present, then they would diverge in this BFSS limit. So when we take the lran limit, this would diverge and would spoil the agreement that we had by just doing the one-loop correction. But it turns out that all these further corrections vanish by a non-renormalization theorem. So the v to the fourth interaction only receives a contribution at one loop and not higher loops. So this makes sure, so this is one example, one of the very few examples where there is an agreement between what we expect from the matrix model and the scattering amplitudes. And it's a check of the conjecture. Note that computing the one-loop term is not enough to check this conjecture. It's important to consider the one-loop term plus a non-renormalization argument so that we can take, in the end, this BFSS limit. In fact, all the computations in the BFSS limit involve the very strong coupling limit of the matrix model. Right? It's stronger than the Toft limit. So we could take the Toft limit of this matrix quantum mechanics, but for the BFSS conjecture, we need a more strongly coupled limit. So in the above computation, for example, the dimensionless Toft coupling has this form, and it diverges, as we said before, when we take n to infinity, keeping the positions fixed. OK, so this is an important point that should be kept in mind. And there is a similar story for the next order in velocity terms, but then if we wanted to go to higher order in velocities, then we are running out of non-renormalization theorems, and well, we would need to actually do a computation. So now we could discuss somehow the simplest amplitude. So the simplest amplitude is the three-point amplitude. Now the three-point amplitude is trivial in M theory, so it's completely determined by the kinematics, by Lorentz symmetry and supersymmetry. And in the matrix model, we have less symmetries, so it's a non-trivial computation to check that we have this amplitude. And it can be done, yes, someone is complaining, but it can be done using supersymmetry, so the three-point amplitude preserves some supersymmetry. And it turns out that using the supersymmetric tricks, you can check that it agrees with the gravity one. Now, it's important for the soft theorem. So the three-point amplitude is important for getting the soft theorems. And it can be combined with some other assumptions to argue that the one will have the Lorentz symmetry. So in other words, if you have amplitudes that obey the appropriate soft theorems, then you will also have Lorentz symmetry. So anyway, what? No. OK. Now, there is a nice story when we compactify some of the transverse dimensions. So we can go from matrix quantum mechanics and to YAML theories in more dimensions. And then we can have some massive BPS states, and they all match between the two descriptions. So using this, we can compactify 5 dimensions, but not more. So let's discuss just the simplest case, so compactifying one dimension. So we have, let's say, the compact spatial now dimension. So now we can imagine these zero branes that, and together with their images, and we can have open strings that go between these zero branes and themselves and between their images. And this build up, essentially these open strings that go between the images.
Is anybody diabetic in here? This is about somebody's blood sugar.
Yeah, so the question is where anyone is diabetic. Apparently it's for...
This is about blood sugar, so if anybody is... Okay, then it's someone outside.
Okay. So the idea is that M theory on a circle of size R9 then becomes the limit of UN super young mills on a circle. So now instead of the matrix quantum mechanics, we have a 1 + 1 dimensional field theory. So with a very similar Lagrangian, except that now we have both time and space, and we also have a Young-Mills field in 1 + 1 dimensions. And in this case, there is an example of a BPS states that we can match between the two cases, which is the D0 brane of type 2A. And this excitation corresponds to 1 unit of electric flux in the field theory. And we can simply see that we put an overall U1 electric flux. And we can track down through all the constants and see that the energy indeed is the energy we expect for a D0 brane. So an interesting limit is the case where R9 goes to 0. In this case, we are supposed to get the weakly coupled type 2A string theory. And one can see that we get the type 2A string theory in Lycon gauge. And this is done as follows. So recall that we have the circle on which the Young-Mills theory is defined is related to the parameters of the theory in this way, so that when we take R9 very small, that circle becomes very large. So we are considering the 1 + 1 dimensional theory on a very large circle. So we are also considering the lower energy limit. And so in this approximation, we can say that the commutator term becomes infinite. And so we go to some moduli space approximation where the matrices are diagonal. And we have a lower energy CFT, which is the symmetric product of RA to the n. Okay, so these are just the combination of diagonal matrices. And then it turns out that this is basically the same. So we have this situation on the circle. We can, when we go around the circle, these n sort of strands can be combined up to a permutation. And in this way, we get the same combinatorics that we get when we have strings in the Lycon gauge with n units of momentum. And not only that, but we can also consider the leading irrelevant deformation, so the thing that takes us away from this free limit. And that operator has a certain dimension. And it's a twist operator that combines two of the strands of the string. And the dimension is such that we get the right dependence on the string coupling. And by thinking about this operator is exactly the operator that gives the interactions in the Lycon gauge string theory, as discussed by Mandelstam. And so in this way, we recover the usual 4-string scattering amplitude, for example. We can get it in this way. So we now return to the 11. So that's a nice check of the BFSS. So in this matrix string discussion, we get, in the weakly coupled limit, we get the results we had in string theory. So now we return to the 11-dimensional case, and we'll make a comment, just a connection between, so we'll make a comment about this bound state that we discussed before. The comment will be about the size of the bound state. So one can argue that this bound state has a size which is of order n cubed times L Planck, well, n to the 1/3, sorry, times L Planck. And this can be shown rigorously by a bootstrap argument. And the scaling with n is expected, is set by the Toft coupling and dimensional analysis. And the important point I wanted to point out is that in the BFSS limit, this size goes to infinity. Okay? So this is in coordinates where we're keeping the sizes that we are interested in M theory fixed. The size of the bound state actually goes to infinity. That means that when we are considering a matrix theory scattering problem, we have each of the D0 branes is some very big bound state that is much bigger than the distances involved in the scattering process. So we have these huge bound states, and they are coming together. There is a no force condition that makes sure that there is no force at very low velocities, and then they interact in some way, and then they go apart. So you see that the supersymmetry is very crucial, and this is also why this regime is hard. So if you wanted to simulate, let's say, this regime in a computer, either classical computer or quantum computer, this is what would make this story quite difficult. Now, one can consider other backgrounds, so not just M theory in flat space. And let's discuss two simple examples. So one simple example is to put some infinitely extended M5 brane that is extended in, let's say, 6 of the space-time dimensions. And if you do that, then you get a quantum mechanics which involves D0 branes and sort of D4 branes. So it's the same matrix model, but with k fundamental hypermultiplets. So that's that's a simple case. Another simple case is to consider, instead of flat space, a plane wave background. And then you get exactly the same matrix model that we had before, except that there are some extra mass terms. So it's a very minor deformation of the matrix model. And we get also the same number of supersymmetries. And in this case, there are some things that become simple. So for example, the bound states the index for the bound states is very simple. You can argue you have all the bound states you want. And there are also many nice results about the spectrum of supersymmetric branes and other supersymmetric observables. In particular, it can be studied using localization because some aspects of this model are very similar to aspects of n equal to 4 super M mills. And recently, also some scattering problems were considered in this model. Now we'll mention something that is not directly related to the BFSS conjecture for 11-dimensional M theory, but it's in sort of the same neighborhood, that it involves also the same matrix model. And so this matrix model is usually called the BFSS matrix model, but we can do other things with these matrix models which are not directly related to the BFSS conjecture. So I'm going now to mention these things. In particular, we can take sort of the standard Toth limit of this matrix model. And if we do that, then this becomes a non-conformal example of the gauge gravity duality. So we can take this matrix model, and we can say that it's dual to the near horizon region of n D0 branes in type 2a string theory. And so this is the near horizon geometry of a charged black hole in type 2a supergravity. And we can take sort of the standard decoupling limit. And in this case, we get a gravity background which contains a time direction, which here is represented as the vertical direction, and also a radial direction, and then there are also some sphere directions. And in this background, we can trust gravity only in some region of the geometry. So the curvature depends on the radial direction, and very close to the boundary, we cannot trust gravity. Very deep inside, we also cannot trust type 2a supergravity, but we can trust gravity in some intermediate region. And so this region that we can describe using type 2a, that's essentially this Toth limit of this matrix model. Now, one comment is that we recall that we were talking about the size of the bound state, and this bound state has a size that is such that the whole gravity region, so the whole region where we can use gravity, is within the size of this bound state. So the branes, the wave function of this ground state extends all the way there. It covers the whole green region that we used in supergravity. Now, naively, when we think about gravity, we think of the d-branes. The reason I'm making this comment is that normally we think in these gravity solutions that the d-branes are here at the origin, okay, at the center of the solution. But the true quantum mechanical wave function of the matrix model extends over the whole region we normally using gravity. We describe using gravity. Now, there are other observables that are natural in this other limit. So these are correlation functions of operators. There have been many interesting studies about the finite temperature partition function. So comparisons with gravity. So these were numerical simulations, classical computer simulations of lattice gauge theory computing calculations of the free energy of this model and comparison with gravity. And this model with non-zero mass terms is also a little bit simpler to think about because you don't have to worry about the branes, these infinite flat directions. And there are many other things one can say about this other limit. Now, let's discuss now an interesting feature of the geometry that is useful for understanding the BFSS conjecture. And that's the fact that if you look at this gravity solution, there is one of the fields is the dilaton, so the type 2a string coupling. And that dilaton goes to 0 at infinity, but increases as you go in the radial direction. So that's basically the value of the dilaton increases as you go to the center of this geometry. So we see that at infinity, the size of the 11th dimensional circle is 0, but the back reaction due to the branes sort of make the size bigger. Okay. So let's discuss now a related point. So imagine that we had an 11-dimensional black hole. So suppose you consider an 11-dimensional black hole written in Kerr-Shield coordinates. So you have something like this. So r is just the full radial direction, so the position in these 9 transverse dimensions plus the 11th direction. Okay? So we have that completely localized black hole in 11 dimensions. And now in preparation for compactification, we consider a periodic array of black holes. So we make a periodic array with the black hole separated along the 11th dimensional circle. And then if the separation is much bigger than the Schwarzschild radius, that metric can be approximated by a sum of this type. So we have this full metric. And then we have an isometry under translations both in x11 and in time. And we can quotient this by a combined translation in x11 and time. So that's the same as the null compactification we were discussing before. So that's the same as making x minus compact. And if we make this direction compact, then when we are very far away from the black holes, that circle is null, so it has 0 size. But when we get very close to the black holes, that circle acquires a non-zero size. And okay. So in the limit that we are taking, the black hole has fixed b plus, b minus, and Schwarzschild radius, but r is going to infinity, and so that the size of this compact direction is much bigger than the Schwarzschild radius. And so as long as we're at finite distance from the black hole, the size of the x minus circle is becoming large. Okay, so we said the size of the x minus circle is 0 at infinity, but at the finite distance from the black hole, that size is finite and becoming large in the BFSS limit. Okay? So we expect something similar when we consider a scattering amplitude, in the sense that the physical size of the circle, we expect it to be large in the region where the scattering amplitude is happening. And that's why we expect to reproduce the scattering amplitudes in a non-compact space, as opposed to the space with a 0, with a circle that is null. So more precisely, something like this. So we have these huge bound states that are colliding, and the physical size of the circle is becoming large in the scattering region. Okay, so I'll now make some comments about the comparison with other ways of obtaining the flat space limit. So another way of obtaining the flat space limit is to consider correlators in ADS and go to a kinematic regime of the correlators where the correlators can be approximated by a scattering process in flat space. So that can be done by taking a suitable lran limit. So this is conceptually similar to BFSS in the sense that we are taking the lran limit of some other quantum system. And it also involves a strongly coupled theory away from the 't Hooft limit. But BFSS obtains the flat space through a different logic than these ADS cases. So in the ADS cases, we have some gravity dual, and then we look at the locally flat space region of the gravity dual. In BFSS, we are obtaining the gravitons as these bound states that we've discussed through this talk. Now, we could say that this point of view for obtaining the flat space limit is a little further developed in the sense that, for example, even the 3-point amplitude is simple, and even some derivatives of the even higher derivative corrections to the 4-point amplitude were found using this limit in combination with some bootstrap arguments and so on. Now, this discussion is also connected to celestial holography. So celestial holography is the idea that we are studying the flat space S matrix, and that we can have perhaps some theory that describes this flat space S matrix. And so the BFSS conjecture gives us this flat space S matrix, and it gives us in a way that does not realize all the symmetries explicitly. Now, we could wonder whether there is some other version of this theory that realizes all the symmetries. And also another question we can ask is whether we can have some theory that does not involve a limit. So here we have to take this lran limit. Is there some other description of celestial holography that doesn't involve the limit? So there is something that we have not discussed, and that's the IKKT matrix integral. This, I think, is a little less, at least by me, less understood than the BFSS model, but it's some other interesting idea for how you could get flat space theory from a simpler model, which is just simply an integral. So in conclusions, we've reviewed this BFSS conjecture for the non-perturbative S matrix, and it's an important window into non-perturbative physics. OK, thank you.
Thank you very much, Juan, for a great lecture. Are there any questions or comments? Please.
If you solve the Klein-Gordon equation in the M-theory description in the green region, there is a 1 over r to the 7th effective potential term. And this 1 over r to the 7th is also common with the v to the 4th over r to the 7th in the one-loop approximation. I wanted to ask if there is a coincidence that in the M-theory description where the BFSS is strongly coupled, you have the same power in the effective potential.
Yes, so that's related to the agreement of the scattering amplitudes for graviton. So that at long distances, the graviton is a massless field, and it obeys the Klein-Gordon equation. And that's why you get this 1 over r to the 7th potential, or term that involves, it's proportional to v to the 4th. And at the level of the one-loop term, you can argue that supersymmetry implies that whatever the correction to the v to the 4th term is, should be a function that obeys the Laplace equation. So it should be 1 over r to the 7th. That's the nature of this non-renormalization theorem. So the non-renormalization theorem is based on the idea that that term should obey the Laplace equation. And so the one-loop integration gives you something that obeys the Laplace equation. It's that particular term, but all higher loops will give you a different power of r, so they cannot be generated.
David?
Yeah.
Juan, I presume you didn't discuss the the perturbative formulation of M-theory, or first quantized formulation, since that still seems hopeless.
What first? I'm not sure what you're referring to.
Well, we could quantize brains.
So quantize, you mean membranes?
Yeah.
Yeah. OK, yes. I did not discuss that. So, so when we can quantize strings, and we can take the limit when strings are weakly coupled and get well, the wonderful results of string theory. one might try to do the same thing for membranes and quantize membranes. And indeed, that was what that paper that I mentioned by DeWitt, Hoppe, and Nicolai was trying to do. So they were trying to quantize the membrane. And what they found was that when you try to quantize the membrane, it's hard to isolate somehow the single membrane. So the membrane can develop little tubes that they were confused about. So with small action, so because the action for the energy for the membrane is sort of the area, right? So you can take a little tube that has small energy and it's a piece of the membrane that can go to infinity. And this was confusing for them. And that in their model was simply that one of the matrices could develop an expectation value for the diagonal part that goes to infinity. In BFSS, that's interpreted as a graviton that is emitted, let's say, from this membrane and goes to infinity. So it describes already the second quantized theory of, of the many particle. So it's the same model, but it's interpreted as describing the Hilbert space of many gravitons, n gravitons, or any number of gravitons. So that's that's somehow the reinterpretation of these older calculations, and somehow the resolution of that apparent problem, or that problem with quantizing membranes.
Okay, we have 3 questions: Shiraz, Igor, and Andy, in that order.
Can I start?
Yes.
As you mentioned,
Okay.
As you mentioned, there's this bulk point singularity way of recovering S matrices.
Yeah.
You could imagine trying to do that directly in the BFSS model by trying to make some sort of correlation function that is tuned in R symmetry directions as well as spatial directions, trying to focus on a bulk point and recovering the...
Yes.
So that would give you another prediction for the relationship between correlation functions in matrix theory and the M theory S matrix.
Yes.
I was wondering what the relationship of that was with the big thing you were looking at.
Yes, so that would be another way of deriving the M theory S matrix that is different from the BFSS one. So,
but would it? I mean, the main difference seems to me to be that in this way you take only a little bit of the. You've got a whole space. Matrix, You take a little bit of that space and scatter it.
Yes.
And I was wondering if this was an analytic continuation of that. That when you take these n's, these ni's large, it becomes this BFSS conjecture.
No, it seems different. It seems like a different procedure, because in the way you were thinking about, you would insert operators that. You would start with one particular, let's say, bound state and consider operators. Maybe the final state might be the same bound state, So it looks to me like a different procedure, but of course it should give the same answer. So there are many. I mean, one interesting thing is that all these various ways of getting the M theory amplitude should give us the same answer.
Okay. Igor?
Yeah, concerning the bound state of this divergence in the size of bound state, so if you consider just the ground state of a string in the light cone gauge, then the transverse x squared also has a divergence, right?
Yes.
Where it's basically the log of n, where n is the cutoff on the total number of modes.
Yes.
So there is some inherent thing, but then it gets cut off when we scatter strings. So this log n gets cut off by the energy of the process. So I wonder if something similar is going on with
Yes.
this.
So the idea is that there is something similar going on in the sense that there is this size of the bound state is some. So if you think about let's say this size as the expectation value of trace x squared, where that's some operator in the matrix model, that is some overall, let's say, additive renormalization constant, and then you can subtract that and then define a new renormalized operator where trace x squared has a finite BEV. And this is common to all examples of all brane theory. So D0 branes, D1 branes, D3 branes, etc.
Yeah, maybe it's an inherent feature of quantum gravity, but in string theory, we don't really subtract this log. I think this log just gives you the Reggie behavior, which is the spreading of the string with higher energy.
Yeah, so for certain observables, we don't see it, and for some others, we do. So, and for the cases where we don't see this, this big size, it's because we are defining some effective theory or effective coordinate. I mean, you could ask this question about what's the meaning of the position of branes inside the, let's say, gravity solution. So that is some effective coordinate, which is not the actual values of x of some matrix, but some effective coordinate that then you could say, well, they are all at the center or separated from the center. But
okay. Andy?
I don't have a mic, so I'll shout.
Yep.
Could you comment on how or if BFSS fits in with the holographic paradigm, which we've come to understand as the idea that we have a theory without gravity on the boundary of a theory with gravity?
Well, it is holographic in the sense that it's a theory for the S matrix, but it's not really defined on the boundary of Minkowski space, right? So it's a quantum mechanical theory, and so if you wish, it does not fit that paradigm the way we understand it for ADS. But maybe that's some lesson that perhaps for the flat space S matrix you might think of a different paradigm. I'm not sure what to conclude about this. So.
Gabriele?
Yep. Can you check soft graviton theorems in the matrix model?
Yeah, so the soft graviton theorem depends on the 3-point amplitude and also on the fact that the whole scattering amplitude has certain singularities when one of the momenta becomes small that is dominated by the 3-point amplitudes. So if you make that second assumption that also in the full non-perturbative amplitude, the singularity will be given by this 3-point amplitude, then you will get the soft theorem.
It's not that if you take one of your gravitons soft, you can connect the n+1 point function to the n point function.
Yeah, yes, but you need to make some assumptions about the structure of analytic, the analytic structure of the amplitude after you've taken the Larsan lemma.
And so do you see any evidence that at high energy you tend to produce many quanta? A lot of inelasticity.
We have time.
No, not really.
Well,
I mean, just intuitively you would think.
Just one question, not two.
Well,
Sasha?
I had Gabriele's question. So is there any evidence in this maybe compactified theory that you produce black holes at high energies in the matrix model? Or what's...
Well, I guess there is some evidence that the D0 brane quantum mechanics contains black holes, at least in this Toft limit. So we would expect that as you go to even lower energies, we continue to get some sort of black hole. Now that hasn't been tested directly other than through, of course, gravity theory, the gravity solution, which I guess you wouldn't call that the test because we are using the gravity description.
Okay.
But I would say the best evidence in that direction are these numerical computations that match the black hole entropy.
One last question from Spenta.
It's a bit maybe premature to ask this question, but what is striking about this model is that it can be written on one slide. So I just wanted to ask you whether it is the complete theory that we are looking for, or what is the connection with this very complicated string field theory that will be discussed later in the day.
Let's wait for later, maybe.
well, I mein, in a certain sense, you could say it's more complicated than the string field theory because, this matrix, you could think about this matrix string theory, and it involves this lran limit and so on. In string field theory, you have some perhaps more complicated looking Lagrangian, but you don't have to take any lran limit. Of course, you could say you have to do level truncation, and then the level truncation is like some kind of lran limit. But yeah, it's a different window into this non-perturbative theory. And, I think it's proven somewhat unwieldy so far, but maybe one of you will, I guess part of the idea of giving this talk is perhaps one of you will say, oh, well, this method that I'm using for something else maybe can be used for this model, and you'll discover some, new result.
Yes, yeah. Anyway, are there any questions from the Zoom community?
There is a question if this three-point computation of yours can be generalized to higher point, maybe in some special kinematics, or is there any generalization of this analysis?
Yeah, one would expect that there are some special, let's say, BPS amplitudes that probably could be used to rederive these higher curvature corrections. I think that probably should be doable.
Any more questions on the Zoom channel? No? Okay, well, let's thank Juan again for a wonderful lecture.